Hello, it's Scott Manley here. Today we are going to be talking about quantum communications in space. Because a lot of people have heard about the Chinese satellite called QUESS, that is the Quantum Experiments at Space Scale, also known as MISIUS. This is a Chinese satellite which has been demonstrating quantum photonics at space scale, generating pairs of photons that remain entangled after travelling 1,000 kilometres. And furthermore, how this achievement will mark the first step to a new generation of super secure communications. Now, the first thing I should make clear is that there's a lot of sci-fi out there that likes to use entangled photons as a way of faster-than-light communication. That's not what's going on here. Yes, there is this magnificent spooky action at a distance where if you measure one photon, it instantly causes the other photon to fall into the appropriate complementary state, but no information can be communicated via that mechanism. No, the satellite is being used to demonstrate the ability to send cryptographic keys between stations. The science of quantum cryptography is primarily concerned with distributing keys in such a manner that they are secure, but you can also tell if somebody was trying to eavesdrop. Now, every time you use the internet, if you're establishing a secure connection, you need to somehow share a secret cryptographic key with the other side of the connection. And this poses a problem. How do you send a cryptographic key across a connection which could be getting eavesdropped on? If you just send the key, then they'll see it, and then they'll be able to decrypt everything that follows. Well, nowadays we protect these keys by using mathematics. Specifically, we use something called public key cryptography. And that is a whole rabbit hole of number theory you can head down, but suffice to say that it allows two sides of a connection to share a secret where a third party eavesdropping could potentially figure it out, but it is thought to be computationally intractable. So while it's not impossible for an eavesdropper to figure it out, it requires so much computing power that the two sides can safely presume that they're not being listened on. However, there's always the possibility that someone comes up with a new, better algorithm for cracking these things. Then you could no longer rely on the intractable problem to protect your secrets. Quantum key distribution, however, allows both participants to share data securely and to verify that nobody is listening. The first quantum communications protocol is known as the BB-84 protocol. It's no relation to BB-8, no, it's named after Charles Bennett and Giles Brassard, who published a paper in 1984 on how to use single photon sending and receiving to securely establish a cryptographic channel. The process relies on encoding information into individual photons using the polarization. So if you imagine a photon flying across the surface of the Earth, it could be oscillating up and down, that would be vertical polarization, and it could be oscillating left and right, that would be horizontal polarization. So let's say that vertical is a 1 and horizontal is a 0. You have a way of encoding information. So if you imagine placing a filter in front of this which only allows through vertically polarized photons, then the detector will only see photons that are vertically polarized. Now, if you rotate the polarizer by about 45 degrees, well, what then happens is you have a 50-50 chance of the photon going through because it's neither vertical or horizontal, and it basically falls down to a quantum process as to whether it makes it or not. This means if the filter is at 45 degrees, then you essentially get random noise. So these two orientations, vertical and 45 degrees, we call these bases. And we allow our sender to encode the bits either in one or the other and swap back and forth randomly for every single photon that's sent. Now on the receiving side, they don't know which basis is being used. They don't know whether it's vertical or whether it's at 45 degrees. So they flip their receiver between each of these positions randomly. And they record what basis was used for each photon. And then, after all the photons have been received, the two sides compare over a public channel what orientation was used. Now, both sides know which ones they agreed upon, and therefore which bits they recorded are the same on both sides. Now, the security of this whole process comes from the fact that if Eve is listening and attempts to intercept one of the photons, Eve doesn't know which orientation to use. So they could receive a photon and retransmit it, but there's a 50-50 chance that they use the wrong orientation and the next photon they send is random noise. So the next step is that the two senders will compare a small number of the bits that they have sent across the wire. And if there is mismatch, if there is noise in this, they know that it's very likely the quantum state is being interrupted. And that could just be a noisy line, or it could be something more malicious in the form of an eavesdropper. Either way, you throw away all your bits and then try again. But if everything looks good, then you can use these bits as a cryptographic key. If you sent enough bits, you can actually use it as a one-time pad, which is provably secure because no bit of the crypto key is ever used more than once. Anyway, the kind of fundamental barrier to how fast this can go is how much noise you have. How many photons make it down your communication channel without having their quantum state modified simply by passing through the communications channel? When we talk about observations, it's not literally someone with a sensor. It could literally just be encountering a weird quantum event inside the communication channel. Literally, when you're sending things down a fiber optic, things can happen to cause your photons to slightly change their state. And then that would look just like an eavesdropper. So in real-world implementations of quantum key distribution, there has been a limit on how far the photons can be sent. Typically, you're talking communications distances of about 100 kilometers. And that's why this satellite demonstration has been interesting, because they've pushed the distance of quantum key distribution from hundreds of kilometers to thousands of kilometers. And this is in part because it's pushing the photons through the vacuum of space, which has a lot less to interrupt the photon's quantum state. Although it still happens in a vacuum, because you can actually get things like quantum vacuum fluctuations, which can interact with your photon and destroy entanglement. And speaking of entanglement, we should actually talk about how the satellite's implementation of quantum key distribution is different than the BB-88 method. They use something called the E91, named after Arthur Eckert, who published a scheme in 1991. Instead of party A, also known as Alice, sending a stream of known photons to B, instead what they do is they have an entangled photon generator that sends one of a pair of photons to each base station. Each base station then performs a similar measurement, picking random detector orientations to receive the photons from the satellite. The satellite doesn't actually know what data it's sending on its photons, but it doesn't need to. So both ends get a random message encoded in random ways, and again in public they will share their detector orientations, match the ones where they both agreed, and then of course they will verify that the distribution of ones and zeros matches what they expect, because if it doesn't match what they expect, it's probably because an eavesdropper has messed up the correlations by introducing something called local realism to the formerly quantum system. Of course, this is all hugely high level, both in terms of the cryptography mathematics and the quantum mechanics. Demonstrations of provably secure quantum communications have been around for over a decade now. This latest development is pushing the distance out further. And it's probably a good thing, because those existing public key exchange systems, those may be vulnerable to new quantum computers. It turns out that many of those problems which are computationally intractable for traditional computers may actually be quite easy to solve for a sufficiently large quantum computer. For example, the problem of factoring large numbers into their component parts. Many cryptographic systems rely on large numbers that are made of the multiplication of two very large prime numbers, and it being very hard to turn that large number back into the two prime numbers that made it up. But one of the first and best known algorithms for quantum computers using quantum qubits is Shor's algorithm, and this is a way of factoring large numbers. Right now, the algorithm has only been demonstrated experimentally with small numbers. In 2001, the first successful attempt was made. They managed to factor the number 15 into 3 times 5. But more recently, a slightly different form of quantum computer was able to factor the number 143. But a couple of years later, a detailed analysis of the computation showed that it had also factored a whole bunch of other numbers, the largest being 56,153. So we can't necessarily rely on the mathematics we use today to secure our communications for tomorrow. And that is, of course, why this quantum demonstration is really fascinating. I'm Scott Manley. Fly safe.